Good morning, everyone. So I'm Shuman Banerjee from the University of Wisconsin, and it is a distinct honor and pleasure to introduce our Athena Lecturer Award speaker, Professor Andrea Goldsmith. So before I invite her on stage, I wanted to say a few words both about the Athena Lecturer Award as well as about Professor Goldsmith. You know, the Athena Lecturer Award is something that was constituted by the ACM Council of Women in 2006, and it celebrates women researchers who have made fundamental contributions to computer science. It's a very elite award, I would say. We have some very big names in our field who have won this before. People like Nancy Lynch, Deborah Estrin, Jennifer Widom, Jennifer Rexford, Shafi Goldwasser, and many others. And it's amazing to have a speaker who will come and speak at our conference, and we have Andrea Goldsmith who will be doing that today. The Athena Lecturer Award winner actually gets to pick the conference where she will speak, and we are grateful that Andrea picked MobiCom, and I think it'll be an engaging talk a bit later today. So her award citation basically describes the following contributions for the award. It's for contributions to theory and practice of adaptive wireless communication, which we all know, and for also successful transfer of research to commercial technology. As you all probably know, Andrea's work has contributed immensely to both the LTE and the Wi-Fi standards or Wi-Fi technologies that have emerged over the years. She's obviously very well known for a lot of her adaptive MIMO work, and that actually led to the founding of this company called Quantenna, which is doing very well. Their technology is used by a large number of companies today, AT&T, DirecTV, Comcast, and many others. And it's a example and a beacon for many of us to follow, because being able to build a theory, implement it in practice, take it to a successful commercialization is a huge challenge, and only few people have done it successfully and many times. So I'm really something to look up to all the time. So Professor Goldsmith is a professor in computer science in the School of Engineering in Stanford. She's the CTO of both Quantenna and a company called Plume Wi-Fi. She has, of course, written a lot of papers, 160 plus journal papers and many more conference papers. She has written 3 textbooks, one of which has been, I believe, translated in 3 other languages, not outside of English. And she's a member of the NAE, which is a really big deal, a member of the AAAS, and a fellow of the IEEE. She was served as the president of the IEEE Information Theory in 2009, and a founding chair of the IEEE TAB Committee on Diversity and Inclusion. And actually, that was one of the other things that was mentioned in the award citation. In fact, the ACM president, Vicky Hansen, was quoted to say that she has done a lot of work to help young women be successful in computer science careers, and that is something we need to do as a community more and more. And so with all that, I would invite Professor Goldsmith to come and share her thoughts on the future of wireless with us today.
Okay, so thank you so much for inviting me. It's really a pleasure to be here, and I'll have a few words at the end to thank the organizers and a few other people. Let me just start. This doesn't work. Okay. All right. So I'm going to start by talking about wireless communication in terms of the big vision, and then I'll get into some more details. Now, I like to think I look really young, but I've actually been working in wireless communication for 30 years plus, so you can do the math. I'm not as young as I look, I like to think. I actually think today is the most exciting time for wireless communication. So I started working in the mid-'80s, and we know that 5G is coming, and there's a lot of new applications. And so that's really what I want to talk to you about this morning is what's new in wireless communication and what we'll be able to do with it that we can't do today. And the reason that I think that wireless is so exciting now is that over the first few generations of wireless communication, it was really all about people either talking to each other over cell phones or accessing information from the internet. And what we're seeing emerge starting in fourth generation Wi-Fi and cellular and going forward into future generations is much more device-to-device communication. So now we're seeing devices that will enable things like automated highways and ubiquitous sensor networks, devices inside our bodies to collect our biometric information, all kinds of things like smart cities where, garbage collection happens because the garbage can is full, not because it's Wednesday. So there's a lot of really exciting new applications that the next generation of wireless can enable, but it's also not clear how we're going to overcome many of the technical challenges. And so that's what I want to focus on in this talk is what do we need to build to enable all these exciting applications, and how are we going to build it? So one of the big challenges for wireless is that there's limited spectrum. So this curve is from a FCC report from a couple years ago, which basically said that as of 2013, we were in 90 megahertz of spectrum deficit for supporting the demand that had grown exponentially over the years, particularly driven by video data. So if that was 5 years ago that we were in 90 megahertz of spectrum deficit, how can we use our devices today, 5 years later? How can we get multimedia over our devices? Well, it's because we're not just using the licensed airwaves to communicate. We're primarily using Wi-Fi. So almost always when Wi-Fi is available, we switch to Wi-Fi. But Wi-Fi has its own challenges, which I'll talk about a little bit later. And so now we're looking at new spectrum. So we're looking at the millimeter wave bands, where there's tens of gigahertz of spectrum. And that's great, but there's a whole new set of challenges in communicating over millimeter wave, as we've seen in some talks in this conference and many other conferences. And then one of the new things that I'm looking at, which I'll talk about at the end of the talk, is molecular communication. So why use electromagnetic waves? Those may not work well inside the body, so maybe we should use molecules. And we've actually built a system in my lab using molecules to send ones and zeros. So there's new ways to communicate, which get around the fact that the licensed spectrum that we use primarily below 6 gigahertz is full. But if we're going to use what's often called the prime real estate of spectrum, which is below 6 gigahertz because of the properties of signals propagating at those frequencies, how are we going to support what's on the horizon in terms of the Internet of Things, which is predicted to have 50 billion devices by 2020? Now, when you've been in wireless as long as I have, or Teresa, who's my dear colleague who followed a few years before me, we've heard a lot of hype before, right? So is this really going to be 50 billion devices, or is it going to be 10 billion devices, or is it going to be hundreds of billions of devices? Well, we don't really know, but actually there is a compelling scenario for the Internet of Things to take off, which I'll talk about on my next slide. Assuming that you're an optimist like I am and say, well, there's going to be at least tens of billions of devices and maybe more, how are we going to support the Internet of Things over cellular when the spectrum was full 5 years ago? And the other challenge with the Internet of Things is not just that we don't have any spectrum for it in the license bands, but the requirements are very different than smartphones. So this is the first generation of cellular where we're not just designing the cellular systems to support much higher data rates. So every generation of cellular from 2G on, when we introduced wireless data, has really been about how do I get better coverage and how do I get higher data rates. Now when we're talking about the Internet of Things, especially things that are powered by batteries and collecting small amounts of data, we don't need gigabits per second of those devices. What we need is extreme energy efficiency of those devices. And the data rates can be low. So this is a completely different paradigm from what we've designed for cellular and Wi-Fi up until now. Another interesting thing about the Internet of Things is that there isn't, in my view, a lot of value to having sensors in my tennis shoes and on my clothing and in my washing machine, unless that I'm doing something with the data that's being collected. So the real value, in my view, of the Internet of Things is the data processing, which is going to take place either at the edge of the network or in the cloud. And how do we get that data up to the cloud and do all the data processing to extract what's valuable about it. Now, that's not necessarily a wireless communication problem, but certainly we need to build the infrastructure to get that data up to the cloud and then, of course, to do the computation, either in the cloud or at the edge. Okay, so how many people have a good definition for the Internet of Things? Raise your hand. I like interactive talks, by the way, so I'm going to ask questions here. I won't call on you. Nobody knows what the Internet of Things is. I mean, we've heard the last day, everyone's talking about the Internet of Things, 50 billion devices, and no one has a definition for it. Okay, so I'll give you my definition, and feel free to shoot holes in it. But my definition, so I want us to be on the same page what we're talking about. The Internet of Things is enabling every electronic device to be connected to every other electronic device and to the Internet. Okay, so this includes, we already have devices that are part of the Internet of Things, our smartphones, now our smart watches, many consumer electronics that already have Wi-Fi. But I'm talking about a much bigger set of devices. Basically, almost anything with an on-off switch that you can put a radio into could be connected to the Internet. And again, as I said before, the value is not connecting all those billions of devices to the Internet, just because you can. It's extracting the data that those devices are collecting and then using that data in a useful way. Now, as I said, I've seen many generations of hyped up applications for wireless networks. Sensor networks were really big, within 5-10 years of me joining Stanford. So in the 2000s, there was a lot of excitement about sensor networks. They were going to take over the world. We're going to collect all this data. We didn't have the notion of big data back then. And none of that really came to pass. So why is it different now? Is it different now than when we used to talk about sensor networks? And I'm actually quite bullish on the Internet of Things because there's already applications where people are making money or companies are making money through the Internet of Things. So if you think about your smartwatches or your Fitbits for health, if you think about smart infrastructures, the light switches and the thermostats that Google has collecting all the data about everything you do, as Monica referred to earlier in her talk. There's industrial applications where we're collecting data from sensors. There's smart highways in Europe where cars and trucks are driving themselves. So there's already today slices, verticals in the Internet of Things where companies are making money. Now, that doesn't mean that any of these are going to be the killer app for the Internet of Things. In fact, people often ask me throughout my 30-year career in wireless, what's the killer app for the next generation of wireless? And I like to say, well, if I knew, I wouldn't tell you. I'd go do a company around it, right? So I'm not going to tell you what the killer app for the Internet of Things is. But the fact that some of these are already making money means there are killer apps out there. And what we need to build, similar to what enabled apps on our mobile phones, was an infrastructure for wireless where any one of these Internet of Things verticals can be successful, can run on this network. That's the challenge for building the infrastructure to support the Internet of Things. Okay, so another question. I've been to many talks, so I do a lot of work in information theory. As you heard, I was the president of the Information Theory Society. Some of my early work that actually gave me the intuition behind adaptive modulation came out of Shannon theory. So if you go back to my slide where I said that we're 90 megahertz in deficit in the licensed spectrum, does that mean that our cellular systems have reached the Shannon capacity of that licensed spectrum? We can't extract any more capacity out of that spectrum, and that's why we are in deficit? Or is it because we're really not designing the best systems to reach capacity that's close to what Shannon predicts? So the question is, are we at the Shannon capacity of wireless systems or not? So I'll take a show of hands. How many people think that we're at or close to the Shannon capacity of wireless systems? Raise your hand. Very few hands. Okay. So how many people think we're not at the Shannon capacity and that we have quite a ways to go to tap more capacity out of the licensed spectrum? Okay. And how many people don't know? Okay, so the people that don't know are the only ones that are right because we don't know the Shannon capacity of most wireless systems. I've been working on Shannon capacity of wireless my whole career, since my early days of graduate school. And for most wireless systems, the Shannon capacity is an open problem. If we don't have a channel model, you can't compute the Shannon capacity. That's true of the molecular communication that I talked about earlier, as I'll revisit later in the talk. Millimeter wave, we don't have good channel models for millimeter wave. So if you don't have a channel model, you don't know what the capacity is. Okay, most cellular and Wi-Fi systems are operating below 6 gigahertz where we have good channel models. If the channel's time varying, this was part of my PhD thesis. The only time you know the capacity of a channel that varies with time is if you know the channel instantaneously at the transmitter and receiver, or at least at the receiver. We never know the channel perfectly, and certainly we can't adapt to it perfectly if we don't know what it is at the transmitter. That's just point-to-point links. As soon as we introduce interference or relays, interference channel and the relay channel have been open problems in information theory for 30 years. And these are like interference channels with one interferer in a point-to-point link and one relay. Okay, so think about a system with many relays or much interference. We don't know the capacity of that. Cellular systems, of course, introduce interference in a controlled way through frequency reuse, so we don't know the capacity of cellular systems unless we treat the cellular system as Cloud RAN, where all the information goes up to some big optimization in the sky that treats all the antennas just as one downlink or uplink. Ad hoc and sensor networks that introduce relaying, we don't know the capacity of those. And then, because I've actually built Wi-Fi chips where things like dollars and complexity and energy consumption matter, none of that comes into Shannon capacity. Shannon capacity assumes that you have infinitely long block lengths, which means infinite energy in processing them and infinite delay constraints. So we don't have a Shannon theory to deal with practical constraints on our designs. Okay, so you might say, well, why bother working in information theory, spend 30 years working on problems that you don't have any answers to? You could say, well, yeah, I should have given up a long time ago. But actually, Shannon theory does provide good design insights, as well as performance upper bounds. And a lot of the work that I've done on adaptive modulation and on adaptive MIMO came out of looking at the Shannon capacity limits of those systems. So even though we don't necessarily know the Shannon capacity perfectly, we can get insights by making approximations or by making simplifying assumptions. Okay, so from Shannon theory and communication theory, there's a lot of exciting things to do in the wireless domain to get to higher data rates for 5G. So again, 5G, and I call 5G, I guess Wi-Fi just renamed itself 6G. So now Wi-Fi is on 6G and cellular's on 5G. But anyway, next generation Wi-Fi and cellular, we're always going to need higher data rates. Even with the Internet of Things where you have some devices that have low data rates, smartphones are always going to want higher data rates, AR, VR. There's many applications where we need to get to higher data rates. So how do we get to these higher data rates? Well, I already mentioned one way is to utilize more spectrum. And the only way to utilize more spectrum is going up in frequency to the millimeter wave band. So I'll talk a little bit about millimeter wave. In order to utilize the millimeter wave band and get around the limitations of that band, we need to use many antennas. So we need to use massive MIMO. So I'll talk about massive MIMO applied to millimeter wave on the next slide. We also need to rethink cellular system design. Okay, so here's another question. Be ready. There's no wrong answers, really. Okay, so when was the concept for cellular system design in terms of base stations laid out in cities and frequency reuse first invented and published? I'll give you a couple decades. So the first cellular system was rolled out in 1983 in Chicago, so it was before that. Okay, so how many people think that the paper that laid out how cellular systems are designed was written in the 1970s? Raise your hand. 1960s. 1950s. 1940s. It was 1948, a paper by D.H. Ring from AT&T Bell Laboratories. And in fact, cellular systems today are designed the same way in terms of the architecture. You go back and read that paper, just look at the picture, figure 1, and it's the same as how we build cellular systems today. Of course, we've gone to smaller cells and heterogeneous networks, but the basic premise of putting base stations throughout cities and reusing frequencies was designed in 1948. So it's really time to rethink cellular system design, and I'm going to revisit that in several slides. And that rethinking cellular system design leads to something that I call software-defined wireless networking. We also need to make the wireless networks green, not only because a lot of the devices are going to be running off batteries that can't be recharged, but also if you're building a cellular system for a part of the world that doesn't have reliable energy, you'd like it to be solar powered, or you'd like it to be extremely efficient in the backbone of the network, not just the devices themselves. Okay, so, and then finally, believe it or not, there is room for new physical layer and MAC layer techniques. You might think, well, you know, a lot of people think that that's dead. There's nothing new to do with the physical layer and MAC layer. We've been working on it for 30, 40 years. So in fact, the physical layer of wireless communication design has been declared dead many times. It was first declared dead in 1971 at a famous workshop, information theory workshop called the Coding is Dead workshop. It was coined that because Bob McLeese gave a talk talking about how coding theorists were all just deriving these incremental results and they were never going to see the light of day. They were completely impractical. And so, you know, everybody should just give up and move on. Coding was dead. That was Bob's talk. And then Irwin Jacobs, who was in the audience, got up and he held up a very small, one of the first VLSI chips. And he said, it's not dead because of this, because of the computation that we're going to enable in VLSI. And indeed, coding theory was not dead in 1971. It's still very much alive today. It was declared dead again in the 1980s. So before cellular system rolled out, so in 1983 was the first cellular system design, and a very famous management company in the US called McKinsey was hired by AT&T shortly after that rollout to tell them whether they should be investing in cellular system technology or not. And McKinsey very wisely, for probably, you know, hundreds of thousands of dollars, told them, no, no, cellular is not going to go anywhere. Really won't be more than, you know, maybe a couple 100,000 people that'll have cell phones, so you really shouldn't invest in this. And so AT&T moved all the people working in cellular into fiber optic communication in the 1980s. Well, of course, cellular took off, and so wireless wasn't dead in the 1980s. And then actually, more recently, in the last decade or so, at least in the United States, maybe not in India or other countries, there's a sense that kind of we've reached a maximum of innovation on the wireless side. There isn't much to do. In fact, many US universities are not hiring people in wireless communication. When I came to Stanford, there were at least 5 professors working in wireless, and I'm the only one now working in wireless. And we're not even seeing that many students interested in it because they all want to do machine learning, you know. So anyway, I think that wireless is not dead. There's a lot to do, as I hope to convince you in my talk. Okay, so let me talk a little bit about millimeter wave massive MIMO. Again, so millimeter wave, officially it's 30 to 300 gigahertz, that range of spectrum, but the sweet spot that people are looking at are around 60 gigahertz up to 100 gigahertz. And the reason this is interesting is, of course, there's tens of gigahertz of spectrum up there. Every wireless, commercial wireless system today that's 6 gigahertz and below would fit into one of these frequency bands. So there's a lot of spectrum, and given the demand for data, we can't really ignore that spectrum. And I give credit to my colleague Ted Rappaport of NYU for really kind of leading the charge to say, yes, it's a difficult set of frequencies to operate in, but we're clever, we're innovative, we can overcome those difficulties, and we can make millimeter wave work. And certainly, he's demonstrated that, and there's many other researchers have followed. Okay, so the problem with millimeter wave, one of the problems, is that power, when you transmit power, say I'm talking to Teresa, the power falls off as 1 over the distance squared to her, but it also falls off as 1 over the frequency squared. Okay, so as I go up in frequency, I get this huge drop in the received power. In fact, that's why generally 5 gigahertz Wi-Fi was not utilized nearly as much as 2.4 gigahertz. Even though it was only a factor of 2 higher in frequency, that meant a factor of 4 lower power at any given location. So the reason that you get this attenuation of 1 over frequency squared is because you're using omnidirectional antennas that's basically propagating the signal in all directions. So you can get around that attenuation associated with 1 over f squared by pointing the beam, by focusing the energy in a very narrow angular dimension. So that's what large antenna arrays do. They basically take this energy, and rather than having it propagate out in all directions, it points the energy in a very specific direction, and as a result, you don't get this 1 over f squared loss in going to higher frequencies. So and there's other benefits to having these large antenna arrays as well. So not only do you not have this large path loss, but you have no fading. Why? Because how do you get multipath fading? Well, it's because I'm talking to Teresa, one of my favorite people in the room, and Monica. Okay, I'll talk to both of them because they're next to each other. Okay, so if I'm talking to both of them, the signal will bounce off the walls and come in to their receiver, shifted in phase from the direct path, and that causes the cancellation, which leads to these rapid fluctuations of your received signal power. Well, if I'm pointing my beam directly at them, there's no reflections off the walls, so the multipath fading goes away. Interference also goes away because I'm talking to them, so it doesn't go to receive because I'm only talking to them. I'm pointing right at them. So basically, all the things that we've worried about in wireless communication theory for the last 30 years go away. There's no fading, there's no interference, there's no path loss. Great. Not only that, but we get all this through these large antenna arrays, and when we go to millimeter wave communication, the antenna elements are smaller because the antenna elements are on the order of the wavelength. So as I go up in frequency, the antenna array elements get smaller and the large array gets smaller. So I like to call this combination of millimeter wave massive MIMO the dynamic duo of next generation wireless. So people that grew up in the US know Batman and Robin, they're, kind of compensate for each other's shortcomings. Same thing is true with millimeter wave massive MIMO. But there's a small caveat, which is that in order to get all this great stuff out of massive MIMO and millimeter wave, I need to know the channel perfectly from every antenna element to every antenna element in the transmitter to every antenna element in the receiver. That's a lot of parameters to measure. And things are changing very quickly. If I don't know the channel perfectly, I can't point my beam because I don't know how to point it. Okay? So unless I can do perfect or near perfect channel estimation, I don't get any of these benefits. And then there's also huge problems with complexity, right? Because you have these large arrays, so you have to do a lot of signal processing. There's hybrid digital and analog processing that are being used to get around some of that complexity. So complexity is a big problem as well. The other thing is that, so suppose that I'm putting this on a side of a building, so I'm not worried about complexity or power. It turns out that this benefit of these pencil-thin beams goes away in many environments. So if I have an object that's between my transmitter and receiver, that beautiful pencil-thin beam goes away. It scatters in all directions. And you also have to now deal with multipath clusters because the beam, if it hits any reflector, it will come in and you still have multipath, so you don't get rid of the multipath problem. So we don't really understand the channel models very well for millimeter wave in terms of the multipath delay profiles or the scattering or the effect of shadowing. So millimeter wave channels are really not that well understood yet because we've just started working with them, and that makes it difficult to build a reliable 5G network on top of a millimeter wave channel, and that's one of the challenges for next generation networks if they're going to integrate millimeter wave. And you can ask me during Q&A if I think that's going to happen, but I won't give it away now. Okay, so there's other new Phi and MAC techniques. Again, it's not dead. For a lot of these IoT devices, we can design waveforms that are energy efficient, which hasn't been something that we focused on. How do we actually design waveforms for millimeter wave channels that have such big bandwidths? We don't know that traditional techniques like OFDM will work well. We certainly know that OFDM doesn't work well when you can't adapt, because you have these huge nulls in some of the subcarriers. So there's other actually new designs of waveforms, something called orthogonal time frequency shift keying, which changes the basis of the modulation design from time frequency to the delay Doppler domain, and that makes it a lot more static and robust. And then we can also come up with variations of subcarrier allocation to do it more efficiently, including having subcarriers that overlap. Detection techniques. Complexity is a big deal, especially for the Internet of Things. So again, if you think about how we've been designing wireless systems, every generation, it's all about higher data rates, which means more complexity in the detection because you have bigger constellations, you have more MIMO antennas. And so how do we go back to, I like to call it kind of back to the future, how do we go back to lower complexity designs that have less energy consumption? And then how do we do these things blind if the channel's changing too rapidly to estimate the channel? And then there's also new access techniques because these IoT devices don't need a dedicated channel. We can have some overlap. So there's many new things to do at the physical layer and at the MAC layer. Okay, now what about ML in wireless systems? This is a bit of a preview to the panel tonight because I'm going to talk about this more then. So I'm not a bandwagon person, okay? So if you had told me 5 years ago that I'd be working in ML, I would have said, no, everybody's working in ML, so I'm going to run the other way, because it's hard to innovate when everybody's working on a given topic. The way I came to work on ML, it feels like a Alcoholics Anonymous discussion, but the way I came to embrace ML was because of the molecular communication work that we were doing. So basically, there's no channel model. That molecular molecules propagate through a channel via diffusion. So there's no linear model that we could use, and there's intersymbol interference. So there was no channel model that we could use in a standard equalizer to get rid of the intersymbol interference. So when there's no model, ML is something to think about applying. We had no model. So we showed, and I'll give some performance results a little bit later, that machine learning trumps theory, because there is no theory when you don't have a channel model, to equalize a molecular channel where there was no channel model, and also to equalize a channel with a known model, a Poisson model, when you don't have perfect channel coefficients. So ML actually can do better than traditional techniques when the channel is unknown or the complexity is too high. And we've also looked at it in joint source and channel coding of text, where the text benefits a lot from machine learning because we don't have good mathematical models for compressing text. So there's a lot of other, so this was, as someone who came into this as a skeptic and said, well, we'll try it because we don't know what else to do. These results gave me some optimism that actually ML can come in many other ways to the design of wireless systems, not only at the physical layer, but also in network resource allocation. And I'll talk about that a little bit more when I get to the network part. Now, we still need theory. So ML, these network layers you can learn in a undergraduate computer science class and then just go run them. But we don't have good theory about how to train these networks for some of these communication system designs, or how to do the optimization of the weights. And we also need bounds, which rely on traditional techniques, to say, is machine learning doing better than theory? Is it doing much worse? And so we still need to understand the underlying theory of these system designs in order to apply ML, in my view. So we're not, as electrical engineers, we're not obsolete yet by machine learning. Okay, so let's get to rethinking cellular system design. As I said, the original design of a cellular system was you put base stations in the middle of cells, and they communicate with the mobile devices that are in the cell, and then when a mobile moves to another cell, you have a handoff. The traditional design, going back to that 1948 paper, is interference limited. So because you're reusing channels in different cells, you reuse the channels as much as possible to maximize system efficiency or efficient use of that bandwidth, and that leads to interference. And so you basically want to reuse the channels that you have to the point where the interference is just barely tolerable for the performance that you need. The capacity, again, is unknown unless you assume that all these base stations are talking to some optimization cloud RAN, which is allocating all the resources in a central manner. But that means there's no interference because you're doing everything centrally. As soon as you introduce interference, capacity is unknown. Now, this notion of being interference limited in cellular systems is no longer the case with many of the technology evolutions we've had over the last few decades. So multiple antennas, as I said, if I point the beam in one direction, I don't interfere with anybody else. So the notion that these systems are interference limited is no longer applicable. We can use multi-user detection, and in fact, even some 3G wideband CDMA systems were using multi-user detection in the base stations to get rid of the strongest interferers. We can have base stations cooperate through COMP. That was part of the early LTE standard. And we can introduce relaying and distributed antennas as well. All of these totally change the interference picture for a cellular system. And while we've introduced those techniques in each generation of cellular when they became available, we never went back and said, should we redesign the architecture of the cellular network to take into account that it's no longer interference limited? That raises interesting questions such as what is a cell, and I'll get to that on the next slide. Now, the other thing that we don't use very well in cellular is dynamic resource allocation, and I'll talk about that as well. So in rethinking cellular system design, if you said, let's throw out that design from 1948 and completely rethink how we should design cellular systems in light of all the technical evolutions we've had at the physical and MAC layer, then you have to ask the question of, okay, how should it be redesigned and to what metric? Are we just going to focus on capacity, which is what all cellular system designs have done up until now? Are we going to look at coverage? So I live off Sand Hill Road in Menlo Park. This is the most expensive real estate in the world. And every time I drive up to the highway 280 on Sand Hill Road, my phone call drops. Okay, and this is the most expensive real estate in the world, and I can't make a phone call on this road. Why? Because there's hills and trees and the coverage isn't very good. Now, I pay a lot of money for my cellular coverage. Maybe I'd be willing to take some sacrifice in data rate to have higher coverage, or maybe pay more. So coverage is an important issue, especially when we look to the Internet of Things doing things like automated highways. I mean, do you really want the call to drop that's telling the car to slow down or stop? So the unreliability of cellular is not going to be acceptable for a lot of the next generation applications. And so we need to fix that in our redesign of these cellular systems. And then energy constraints, as I said, for IoT devices. You want these networks to be designed so that the antennas are as close as possible to the device, because that's how you reduce the transmit power. Okay, so if we're just going to focus on capacity, because we at least know everybody wants higher data rates, small cells are the solution to increasing cellular system capacity. That's been known for a long time. It was a result that I worked on with my first PhD student in the mid-90s. It's also part of the cellular standard in terms of hat nets. And the basic idea why you get higher data rates with smaller cells is that if you design a system so you can support, say, 100 users in a cell, as the cell size shrinks, you're supporting those same 100 users in a much smaller area. So the overall capacity of the system goes up. Now, we can't just build networks of small cells because we need coverage. And when you roll out a new generation, say 5G in cellular, you have to first blanket the city with coverage of 5G, and you do that with the large cells, and then you fill in with small cells where you need more capacity. Now, these small cells are, you know, even though we've been working in small cells and predicting, in fact, my second startup was going to do resource allocation for small cells, but it never happened because small cells weren't rolling out very fast. They are starting to now, and you can't deploy these small cells in the same way large cells are deployed, where you have, you know, a team of people, usually guys, that go and put the cell up and run around and take measurements and tweak the parameters, and then they go away. You need dynamic optimization. Okay. The other reason why small cells hasn't really taken off is because of Wi-Fi. So why have this, you know, 90 megahertz of spectrum deficit from 2013 not hurt us? It's because of Wi-Fi. Wi-Fi is the small cell of today. It's the primary access mode. I mean, if you're anywhere where there is a Wi-Fi signal, you switch to Wi-Fi because there's higher data rates and more spectrum. The physical layer design is the most advanced, way more advanced than cellular. You can get up to 10 gigabits per second with Wi-Fi today. But there's a big problem with Wi-Fi, which is the multiple access problem. So whenever you're in a dense environment, because we're using a multiple access mechanism, carrier sense multiple access, that was designed in the 1970s, we don't have a good way to share the channel in a distributed way with Wi-Fi, at least with kind of off-the-shelf Wi-Fi. Of course, there's enterprise Wi-Fi and other types of Wi-Fi that modify 802.11 to do better access. But in the generic 802.11 standard, we don't have a good way to do Wi-Fi, and the result is that when you're in a crowded environment, you either can't get on the network or you get very poor performance. So what can we do about this? Well, this notion of using SON, which is optimization in the cloud to do resource allocation for small cells, we can also apply it to Wi-Fi, and that's what Plume, my second company, did. Once we figured out small cells aren't going anywhere, let's pivot to Wi-Fi, so we started doing this for Wi-Fi. And the idea is that you can take kind of standard APIs for Wi-Fi chips and collect, you know, standard information like RSSI and packet error rate. In fact, we were using the MAD Wi-Fi that Athena developed to collect some of these parameters. And then you do the optimization in the cloud. So it looks a lot like a cellular network where you're doing centralized optimization, but you can do this with any off-the-shelf Wi-Fi access point as long as you can get access to the parameters. And we showed that you can actually do much better in terms of reducing the variability of Wi-Fi, because obviously when you're doing centralized optimization, it's much better than distributed optimization. So we got much more consistent performance of Wi-Fi and a much lower outage probability by doing this optimization in the cloud. So why not use this idea for all wireless networks? Okay, so when we go to vehicular networks, 802.16, or Wi-Fi or millimeter wave, why not use this optimization in the cloud to not only optimize within each one of these wireless networks, but also if you're, for example, sharing spectrum across Wi-Fi and cellular, you can use this optimization in the cloud to do that in the most efficient way. So that leads to this notion of what I call software-defined wireless networking, where you have the application layer, which is the application you're trying to send over some set of wireless networks. And as a user, you don't really care if your phone is on Wi-Fi or millimeter wave or cellular. You just want it to work and pay the minimum amount of money. And maybe you'll pay a little bit more if you're looking at an application like AR/VR versus, sending a text message. So this unified control plane can not only control the parameters of each one of these networks, but it can allow seamless handoff between the networks. So it could allow you to go from Wi-Fi to cellular and back again, which today you have to shut down your application in order to do that. And it can allow sharing of spectrum. So if you've got today, there's a lot of concern about LTE moving into the unlicensed band, so unlicensed LTE, because Wi-Fi is worried that this is going to crunch its spectrum. But if you could do this sharing in an intelligent way through a centralized control plane, there'd be less concern about that. And in fact, in the Shangri-La of designing networks in this way, you could just forget about all wireless standards in general and just throw a bunch of antennas out there and let the unified control plane figure everything out in terms of how to use these antennas at different frequencies in the most effective way. So this is my Shangri-La of how we should design wireless networks. Of course, there's some challenges. And one of the biggest challenges is the algorithmic complexity. So some of the early work I did in resource allocation for cellular back in the 90s when I was at Caltech was doing frequency allocation for second-generation systems. And that is an NP-hard problem. It's a graph coloring problem, so it's an NP-hard problem. Now, we have a lot more techniques at the physical layer. We have multiple antennas, we have power control, we have hierarchical networks of large and small cells. So I call this now an NP really hard problem, because it's not just NP hard, it's much harder than that. But fortunately, there's a lot of advanced optimization tools that we can use to approximate these NP hard problems or non-convex problems and solve them. But I think what's interesting in this optimization, and there's not a lot of theory behind this, is combining cloud optimization with what I call fog optimization. So what's fog optimization? It's where you take neighborhoods of base stations or access points in the network that are close together, because those are the ones that are interfering with each other, and you do the optimization in the fog rather than in the cloud. If you do everything in the cloud, the complexity is too high and the latency is too high. If you do things in a distributed manner, as we saw in the SON for Wi-Fi performance results, you get suboptimal performance. It's much worse than centralized optimization. But the question is, can we do this optimization through neighborhoods and get almost as good performance as in centralized optimization? And by the way, also with these small cells, we need to think about optimizing the caching and the edge computing, but that's a separate problem that we haven't looked at yet. So we actually, this is hot off the presses. We literally just submitted this to ICC a couple days ago, of looking at fog optimization versus centralized optimization. Now, to do the fog optimization, first you have to cluster which base stations belong to which neighborhood. So you have to form the neighborhood. So we looked at different clustering techniques. And then once you have your clusters, you do the optimization. In this case, we're looking at power control. And so if you only have one virtual cell, it means it's centralized optimization. You're optimizing over all cells. As you get more and more virtual cells, that's basically the number of neighborhoods that you have. So it's getting more and more decentralized. And we found that we only lost 20% in terms of the total sum rate by going from fully centralized optimization to neighborhood optimization with 6 virtual cells consisting of 6 base stations. So each base station was doing its own optimization. So this is very promising for reducing the complexity of doing the optimization in the cloud versus in the fog. We also want to look at redesigning cellular networks to make them more green. And there's, again, this is a completely different way of thinking about designing these systems. I won't get into the details, but we're not going for higher data rates anymore. We're going for extreme energy efficiency. Okay, let me skip this. Another interesting problem with these severe energy efficiency problems is where should the energy come from? So we know when we charge things through batteries that we have a constant source of power until the battery runs out. What about wireless power transfer? So if we're sending data, why not send energy along with the data and harvest the energy of the signal that you're receiving, not just to get the data, but to get energy? And then there's energy harvesting, where you collect energy from the environment. This, again, completely changes the principles for communication design, because you need to wait to get enough energy to send your data, and should you wait to send a very large constellation very quickly so that you can shut down your electronics quickly? So there's a lot of interesting challenges in doing energy-constrained communication. Okay, last two quick topics are chemical communications. So the way I came about doing this was I had a student who was a PhD student in York University. He built this chemical communication platform, and he wanted to do a postdoc, and I thought, this is really cool, because it's a completely greenfield area of research. How do you send bits using molecules or chemicals instead of using electromagnetic waves? So we need new channel models. We need to figure out how to do modulation and coding and networking in terms of relays, mitigating the channel impairments, et cetera. Okay, so, and the applications can be from the microscale, and the thing that I think is most interesting here is the in-body communication. If you don't want to use electromagnetic waves, which can damage your organs, you could use chemicals, you know, and again, the data rates may not be very high, but you're just turning on and off or adjusting parameters of artificial organs or drug delivery systems. And then in macro scale environments where you can't send electromagnetic waves efficiently, like underwater or through pipes, you can also use this kind of technique. And what my postdoc Nariman did in his PhD thesis was he built this chemical communication system using vodka and on-off keying. Okay, so he was in Canada, so, you know, vodka's popular there. And so the idea was you want to send a 1 bit, you send vodka. You want to send a 0 bit, you send no vodka, and you use a breathalyzer on the other end to determine vodka or no vodka, 1 or 0. And he got a whopping ½ a bit per second with this original system. And this was a fan-enhanced channel, which means you blow so that the chemicals go a little bit faster. So, you know, you might think, okay, a ½ a bit per second, well, we're talking 10 gigabits for wireless, this isn't very interesting. But again, think about turning on and off an artificial organ, or adjusting its parameters, or turning on a drug delivery system. This is a fine data rate. So when Nariman came to Stanford, I said, okay, well, let's look at how we can improve this system. And so we said, well, one of the problems is that with the vodka, basically what happens is that the vodka takes a long time to dissipate in the channel, so it hangs around the channel for a long time, and the breathalyzer gets saturated. You know, like if we go out tonight to the banquet and drink a lot, you know, we're not going to be able to detect much. Same is true of these detectors, because they get saturated with the chemical. So we built a system with acids and bases that cancel each other out, so that if you send about an equal number of 1s and 0s, they cancel out the acidity or the base properties of the chemical, and so you get back to a neutral state. And the other thing that we did new was using this notion of equalization. So if you send a long string of 1s or long string of 0s, those chemicals stick around and they interfere. And here's where we applied machine learning. So this was our first application of machine learning, because there was no channel model, and we actually got a 10x improvement in data rate by applying machine learning to this equalization. So that was the first time where I said, okay, well, maybe there is something to machine learning. So we built a system with vinegar and Windex, and the Stanford report had a great article about this, and there's a video on it showing us sending this text message using Windex and vinegar, and I think the tagline was, this is not likely to replace text messaging for undergraduates anytime soon, but it's still a cool technology. And the last thing I'm going to talk about is the brain as a communication network. So about 9 years ago, I joined a proposal for an NSF Center on the Science of Information, where we wanted to look at applying the techniques of signal processing and communications beyond information technology to biology and data science and economics. And I said, okay, of all those fields, which I know very little about, I haven't studied them since my first years as an undergraduate, what looks most like something I know? So I said, well, the brain looks like a network, right? I thought it was a wireless network. That's how little I knew about it. It's actually a wired network in terms of how the electrochemical signals travel. So I said, well, let's look at applying our techniques of signal processing and communications and information theory to the brain. So it took us a long time to figure out what to do, but we ended up focusing on localizing the seizure onset zone of epilepsy. So what happens with an epileptic seizure is that there's typically a neuron or a small region of neurons in the brain that start oscillating wildly. And because of the way signals propagate in the brain, that region of neurons, their signals end up propagating to neighboring neurons and then neighboring neurons, and eventually you have enough neurons that are oscillating in this rather chaotic way that causes a seizure. And if the epilepsy is drug resistant, the only way to cure the seizures is to go in and cut out that region of the brain, okay? So figuring out what region of the brain to cut is a pretty important problem for doctors that focus on this kind of epilepsy treatment. So we said, well, can we use our signal processing techniques? Because what's happening is there's a causality effect. The signal is propagating out from one region to other regions. And the way the doctors localize this seizure onset zone is they put these sensors on the surface of the brain under the skull, and they measure the signals. So this set of curves is the signals coming out of the sensors. And somehow the doctors are able to look at this data and see where the seizure onset zone is. So we said, well, can we apply something called directed mutual information, which is an information theoretic algorithm, to reverse engineer through causality where the signal originated? And so we applied that to data sets, and we found that our algorithm beat the doctors in the sense that our algorithm identified a smaller region than the doctors had, and it matched the doctors in, I think, 85% of the cases. And what we want to do now is go back and look at the 15% where we didn't match and say, well, if the doctors went and cut out the zone that the doctor predicted, did it work or did it not? Okay, so that's the last topic. So let me just wrap up quickly. So it's a very exciting time in wireless communication. I think the technology will enable new applications that will change people's lives worldwide. You know, usually you have to say that when you write a research grant because you have to say why it's important beyond the technology, but I actually really believe that the next wave of wireless is going to have a huge impact well beyond what we can do today. We need to build networks that will support high data rates for some users and extreme energy efficiency for others. There's a lot of technology that needs to be developed for both of those, to support both of those, as well as data computation in the cloud to make Internet of Things valuable. I think machine learning is a promising new tool to use, and I'll talk about that more in the panel tonight. And then also, the communication tools and modeling techniques that we use every day in designing wireless systems can provide great breakthroughs in other areas of science. So 2 quick final slides. First, I'm so honored to receive this award. This is my first ACM conference, actually, and so it's an honor to be here. And to receive the Athena Lecture Award, it really means a lot. So I have to thank ACM and my nominators and the committee that chose me. Thank you so much. It means a lot to me. I want to thank MobiCom and the organizers for inviting me. It's really a pleasure to be here. I was last in Delhi in 1995, so it's changed. I didn't have my own private driver back then, you know, I was kind of a backpacker, so it's a different experience this time around, and your hospitality has been fantastic. Thank you so much. And finally, you know, it's wonderful to win awards. It's very rewarding, but that's not what gets me up every day, or most of us up every day. So this award belongs to all my students and collaborators who did almost all the work and are the best part of my job. And my last slide is Happy Halloween, because it is Halloween back in the US.